Welcome to my video Tomography 205. My message today is a bit mind-bending. First I explain how pixel-based tomography models can be approached without matrices. And then I show how to construct tomographic matrices using a matrix-free trick. Enjoy the mathematics. Recall the imaging model from my video Tomography 203. We have 12 by 12 pixel grid and 11 parallel beam measurement directions. A target with two non-zero pixels produces a sinogram with two sine curves. This is how the MATLAB command radon works. It takes two inputs, pixel image and X-ray angles. The output is the sinogram as an image. Our goal is a linear measurement model AX equals M, where the matrix A implements the formation of the sinogram. This process can be a bit confusing because sometimes X and M are treated as images and sometimes as vertical vectors. Let's take a look at the flattening and reshaping steps necessary for moving between vectors and images. I demonstrate them first with the 3 by 3 pixel grid we saw in the video Tomography 204. This is the flattening step in MATLAB style. We organize the columns as a vertical vector. The reshaping step collects the columns back to image form in the same order in reverse. Now let's look at the 12 by 12 pixel grid. The numbering runs from 1 to 144. Let's again color every other column in red. This is the way how a 12 by 12 image is flattened to a vertical vector with 144 elements. And we can also reshape it back like so. Now we can map any image style 144 vector into a sinogram style 231 vector as follows. Reshape the vector X into a 12 by 12 pixel image. Apply the radon routine to get a sinogram of size 21 by 11. And then flatten the sinogram into a vertical vector. Note that all of this happened without any matrix A. We just used the tomographic radon routine. When solving large tomographic problems, such a matrix-free process can be passed on to an iterative solver, allowing efficient computation of reconstructions. But funnily enough, we can use this matrix-free approach for constructing tomographic matrices. Now, it's not a good idea to construct the matrix A by hand for the 12 by 12 pixel grid or larger ones, because it is a huge job. There are software packages for doing that. I will list some of them in the video description. But sometimes it's nice to construct a matrix for testing purposes in a simple way, even if it's computationally a bit inefficient. And I have a trick for that. Let me first explain it with a general 2 by 2 matrix. Let's multiply the first unit vector with our 2 by 2 matrix. This is what we get. The second unit vector gives such a result. We can collect the two calculations together and make a general observation. Multiplying the nth unit vector with some matrix picks out the nth column of that matrix. Let's bring the column picking trick to the context of tomography. We again start with the first standard unit vector in the Euclidean space R144. Reshaping it into a 12 by 12 image gives one non-zero pixel in the top left corner. We can use the radon routine for calculating the sinogram as an image. Finally, we flatten the sinogram to a vertical vector with 231 elements. This is the first column of the tomographic measurement matrix A. We continue with the second unit vector, giving us the second column of A. Going on systematically takes us finally to the last column. Looping over the columns constructs the whole matrix for us. Now that we have our matrix A constructed, let's take a look at the block structure it has. There are 11 flat and wide blocks, one for each measurement direction. There are also 12 thin and tall blocks corresponding to the columns in the image matrix. This method of constructing matrices is very flexible. It works with any geometry, fan beam or parallel beam or so, and also it readily accepts any kind of limited data like limited angle or exterior tomography or sparse angle or interior tomography. Whatever the geometry is, the matrix always has one row for each measured X-ray. See you in the next video.